Motion questions. Perhaps the largest category of word problems concerns moving things and the related quantities distance, rate or speed, and time. These are all related in one extraordinary formula, D equals RT. Some people will like to remember this as the dirt equation. Thinking of that, well, you know, things move on the ground and the ground is made of dirt. That helps some people to remember this formula. So in that formula, it relates D, distance, R, which is rate or speed, and T, which is time. Each one of these quantities has units, and it's important to keep track of the units in your calculations. The units for rate determine the units of both distance and time. If rate is in miles per hour, distance must be in miles and t must be in hours. If rate is in meters per second, distance must be in meters and time must be in seconds. Similarly, if you know the units for distance and time, that determines the units for rate. The same length unit and time unit need to be used in the units of all three. Notice that D equals RT is already solved for distance, and we can easily solve for rate or time if we need to. If we divide both sides of that initial equation by t, we solve for rate. So rate equals distance divided by time. Alternately, go back to D equals RT, divide both sides by rate, and what we get is t equals d over r. Time equals distance divided by rate. And that's solved for time. It's very important to be comfortable moving back and forth between any of those three forms. Let's do a few simple calculations for practice. So pause the video and then we'll talk about these three questions. Okay. The first question, what is the speed of someone who covers 240 miles in 6 hours at a constant speed? Well, we're given distance, we're given time, and we're looking for rate. So we want the version that is solved for rate. Rate equals d over t. And then we're just going to divide the distance by the time. 240, well, 24 divided by 6 is 4, so 240 divided by 6 has to be 40. And that would be 40, and then miles over hours, that's miles per hour. 40 miles per hour is the answer. Second question, how far does someone moving at 8 meters per second move in 40 seconds? Here we're looking for the distance, so we want the form solved for distance. D equals RT, the original form. We're simply going to multiply the rate, 8 meters per second, times 40 seconds. Well, 8 times 4 is 32, so 8 times 40 has to be 320. And meters per second times seconds gives us meters. So this should be 320 meters. Finally, the third question, how much time does it take to move 300 feet at a speed of 20 feet per second? Well, here we're looking for time. We know the distance and we know the rate. So we need the form that is solved for time. Time equals distance over rate. Now we're going to divide that distance by that rate. Of course, we can cancel the zeros. That would lead us with 30 over 2, which would be 15. That's the number. And of course, the time unit is seconds. So time has to be in seconds. It has to be 15 seconds. Now, each one of those is too easy in and of itself to be a complete test question, but these solutions demonstrate the fundamental skills you will need. In other words, in any distance, rate, and time problem, you're going to have to typically be doing one of those calculations a few times. Okay, now I need to find this distance. Okay, now I need to find that time. So you're going to be putting together different rates and different times and doing these calculations multiple times to get through a larger test question. What if the units given in the prompt and the units for which the prompt asks are inconsistent? So you might be given 2 different units in the prompt, or you might be given 1 unit in the prompt and then ask for another unit. What do we do? Well, we need to change units, and we use a unit conversion such as 1 hour equals 60 minutes or 1 foot equals 12 inches. Those are 2 very standard unit conversions. Often the test will give you the conversions for any that aren't very common. Any unit conversion can be written as an equation, but it can also be written as a fraction equal to 1. So we can say 1 equals 1 foot over 12 inches, or 1 equals 12 inches over 1 foot. You see, that's awfully useful. If we have something equal to 1, that means we can always multiply or divide by that, and we don't change the fundamental values. So much in the same way, you can always multiply a fraction, say, by something like 7 over 7. That doesn't change the value of the fraction because you're really multiplying by 1. Much in the same way, you can take any quantity and multiply by something like 1 foot over 12 inches, or 12 inches over 1 foot. You can multiply by either of these, and it wouldn't change the value either, because this is also multiplying by 1. So here's a question. Pause the video and then we'll talk about this. A lichen advances 4 centimeters each year across a rock slab. So 4 centimeters per year, that's the rate. If this rate remains constant over time, how many years will it take to cross 30 meters? So here we're looking for time. So we want to solve for time. Time equals distance over rate. But we have to take care of the inconsistent units because we have a speed involving centimeters, but a distance in meters. And of course, the question is nice enough to tell us that 1 meter equals 100 centimeters. So our rate is 4 centimeters per year. Our distance is 30 meters. And the easiest thing to do is just right away change that distance to centimeters. So we're just going to multiply it by 100. We're going to multiply by 100 centimeters over 1 meter, cancel the meters, and we get 3,000 centimeters. So that's the distance, and now distance and time are in the same units. Time equals distance divided by rate, 3,000 divided by 4. 3,000 divided by 4 is 750, and the time unit is year. So this will be 750 years. Here's another question. Pause the video and then we'll talk about this. A car moving at 72 kilometers per hour moves how many meters in 1 second? So we're told that 1 kilometer equals 1,000 meters. Well, we also have to change hours to second. Well, we know that 1 hour is 60 minutes, and each minute has 60 seconds per minute. So 60 times 60 is 3,600. 1 hour equals 3,600 seconds. That's actually a very good number just to have memorized because it does show up often enough that it's good that you don't have to recalculate it, just to know that 1 hour is 3,600 seconds. Okay, well now we can say 72 kilometers over hours. 72 kilometers would be 72,000 meters, and 1 hour, as we just saw, is 3,600 seconds. So really this speed is 72,000 meters over 3,600 seconds. We'll cancel some zeros. Now notice that 72 is just 2 times 36. So 72 over 36 is 2. 720 over 36 has to be 20. So 20 meters per second. So it moves 20 meters in 1 second. In summary, D equals RT is the fundamental equation for moving things. Note how to solve this equation for R or for T. It's already solved for D. You want to be able to solve it for each of the 3 variables. Keep track of the units of numbers when you plug in. Don't ignore units. If you pay attention to units, that will really help you. Unit conversions can be written as fractions equal to 1. We can multiply or divide by them. That's very convenient. Know the common unit conversions and change units so that all units in the problem are consistent. The first thing I'll say is, as you study for the test, it's important to reflect from time to time on the perspective of the person who writes the test. The more you can understand the perspective of that person, the more insight you'll have into the questions. In particular, people who write the questions for the test love questions that have very predictable traps, because those predictable traps make it very easy to separate the folks who know their stuff from the folks who don't. So this is a good example here in the topic of average speed. This is one of the test's favorite kinds of word problems because it contains some very predictable traps. Normally, if we need the average of two numbers, we simply add them and divide by 2. That's normally how you'd find an average. That is not how to find the average velocity, but that is the tempting trap into which so many test takers fall. Here's an example. Bob drove 120 miles at 60 miles an hour, then another 120 at 40 miles an hour. What was his average speed for the trip? In a moment we will solve this problem, but first let me point out the trap. So many test takers will simply average 40 and 60. Of course, the average of 40 and 60 is 50, so they're going to say that the average speed has to be 50 miles an hour. That trap will always be listed as an answer choice. Avoid that trap. So 50 miles an hour is the wrong answer. It is not the answer to this question. But so many people fall into the trap. They average the two numbers and they think that's how you find the average velocity. And that is not how you do it. To solve a question of this sort, we use d equals RT, which is true for each leg of the trip and true for the trip overall. So there's a d equals RT for the first leg, there's another d equals RT for the second leg, there's also a d equals RT for the trip as a whole. In particular, average velocity equals total distance over total time. So the r of the total trip, that is the average velocity, and that is the total distance divided by the total time. That is the formula for average velocity. Often we have to find the total distance by adding the distances of the individual legs and find the total time by adding the individual times. Now we're ready to do this problem. So pause the video and then we'll talk about this. Okay. So in the first leg, he drove 120 miles. He drove at a rate of 60 miles an hour, so that would be a time of 2 hours. So now we have d, r, and t for the first leg. Let's calculate this for the second leg. For the second leg, 120 miles divided by 40 miles an hour, so that took 3 hours. The total distance is 120 plus 120, that is 240. The total time is 5 hours. So 240 divided by 5, I'm actually going to multiply numerator and denominator by 2, so that I'm dividing by 10 instead of dividing by 5. That makes it much easier. And this divides to 48 miles per hour. 48 miles per hour, not 50 miles an hour, is the correct answer. Sometimes the problem won't give you all the numbers. For example, Cassandra drove from A to B at a constant 60 miles an hour speed. Then she returned on the same route from B to A at a constant speed of 20 miles an hour. What was her average speed for the whole trip? Of course, the trap answer is just averaging 60 and 20. That would be 40. So it is true that 60 plus 20 divided by 2 is 40. That's how you'd find the average of those two numbers. But for speeds, we cannot find an average speed just by averaging the individual speeds. So that is a trap answer. And again, that trap answer will always be listed as an answer choice, and there will always be large numbers of test takers who fall into this trap. If you can avoid that trap alone, that sets you apart from so many other test takers. All right, so now try this, and then we'll talk about it. Okay, so this is tricky. One approach is to just call the distance a variable. D equals the distance from A to B. So the first leg, the time, would be d over r, that's d over 60. For the second leg, the time, again, is d over r, that's d over 20. Those are the two times. The total time is the sum of those two times. We'll find the common denominator, combine them. We can simplify a little bit. So the total time of the trip is d over 15. The total distance is 2d. So the average velocity is 2d over d divided by 15, which is 2d times the reciprocal of the fraction in the denominator, 15 over d, notice the d's cancel. And this would always be true. If you pick a variable for the distance, it will always cancel. And what we get is 30 miles an hour. And that is the correct average speed. Now here's another approach, another perfectly valid approach. We could just pick a value for the distance. So let's say that the distance is something nice and round, like 60 miles an hour. Well, she travels at 60 miles an hour going there. She covers 60 miles in 1 hour. Coming back at 20 miles an hour, it will take her 3 hours to go 60 miles an hour. Well, that means the whole trip took 4 hours, and she covered 120 miles in 4 hours. That gives us an average of 30 miles an hour. Here's a test-like practice question. Pause the video and then we'll talk about this. An airplane has a 3,600-mile trip. It covers the first 1,800 miles of the trip at 40 miles an hour. Which of the following is closest to the constant speed the plane would have to follow in the last 1,800 miles so that the average speed of the whole trip is 450 miles per hour. So 450 miles per hour is the average of the whole trip. 400 is the speed in the first half. So, of course, what are people going to fall into a trap about? They're going to think, well, what two things do you have to average to get 450? Well, if you average 400 and 500, they would average to 450. Therefore, 500 must be the speed in the second half of the trip. So that is our suspected trap answer. Again, it's listed, we expect it to be listed, and we expect it not to be correct. So let's go about this. In the first leg, we know the distance, we know the rate, we can figure out the time. For the whole trip, we know the distance, the rate, we divide, multiply top and bottom by 2, cancel, we know the time. That allows us to figure out the time of the second leg. The time of the second leg, we subtract, that has to be 3.5 hours. So the speed in that second leg has to be the distance of 1,800 miles, divided by 3.5 hours. Okay, well, that would be hard to do without a calculator, but we can use a little bit of estimation here. First of all, we'll multiply top and bottom by 2, so we get 3,600 over 7. Notice that 3,600 over 7 has to be bigger than 3,500 over 7. 3,500 over 7 is 500 miles an hour, so clearly the speed is larger than 500 miles an hour. Also, 3,600 over 7 has to be smaller than 3,600 over 6. Well, that equals 600 miles an hour. So that means that the speed, the answer, has to be between 500 and 600 miles an hour. Well, estimating like this, we can eliminate enough to narrow down to a single answer choice. And in fact, that alone eliminates down to the answer choice D. So that would allow us to solve the question. Alternately, we could calculate this. We could do a quick calculation without a calculator very easily just by saying, let's think about this, 3,600 over 7. Well, that's 3,500 plus 100. We'll split the fractions up. That first fraction is clearly 500. And how many times does 7 go into 100? Well, it goes into 100 about 14 times. So that's about 514, and that's enough to get us our answer. In summary, when finding the average velocity, do not fall into the trap of thinking it's a simple numerical average of two things. You have to find d and t of each leg of the trip and add across the legs to find the total distance and the total time. The average velocity equals the total distance divided by the total time. Multiple travelers and multiple trips. Some motion-based problems involve more than one traveler or trips of more than one segment.
We already saw a little of this in the previous video on average speed. The basic strategy is that each traveler and each trip gets its own d equals rt equation. And sometimes we have to set up multiple equations and then use the techniques that we've learned for solving two equations with two unknowns. Here's a practice problem. Pause the video and then we'll talk about this. All right. Martha and Paul started traveling from A to B at the same time. Martha traveled at a constant speed of 60 miles an hour and Paul at a constant speed of 40. When Martha arrived at B, Paul was still 50 miles away. What is the distance? So notice, first of all, that the time, we'll just say that time is the time from the starting point to when Martha arrived. And so Martha, of course, traveled that whole distance d. But what about Paul? Paul didn't get all the way to D. He was still 50 miles away, so that is D minus 50. And so the distance that we're going to use for Martha is D. The distance we're going to use for Paul is D minus 50. And so now we have something to plug in for distance and rate and time. So for Martha, distance D, rate 60 times T. For Paul, D minus 50, because at that same time he was 50 miles short of the city of B. So he went D minus 50, and his speed was 40, and the same time T. Well, notice now we have two equations with two unknowns. The first one is solve for D, so just plug it into the second one. We get 60T minus 50 equals 40T. Add 50 to both sides, subtract 40T from both sides, we get 20T equals 50. Divide by 20, we get 5 over T equals 5 over 2, or 2.5 hours. Now we have to solve for T, now that we have the value, solve for D, now that we have the value of T. Plug this in, it makes sense to plug it into the first equation. D equals 60 times 2.5. Well, 2 times 60 is 120. 0.5, or 1/2 times 60 is 30. 120 plus 30 is 150, and that's the distance. Here's a practice problem. Pause the video and then we'll talk about this. Okay, Frank and Georgia started traveling from A to B at the same time. Georgia's constant speed was 1.5 times Frank's constant speed. When Georgia arrived at B, she turned around immediately and returned by the same route. She crossed paths with Frank, who was coming toward B, when they were 60 miles an hour away from B. How far away are A and B? So I'm going to use the variable D for the distance between A and B. So that's the variable that we're looking for. For Frank and Georgia, Frank has a rate of R. Georgia has a rate of 1.5 times that, so 1.5 R. Georgia goes all the way from A to B, and then she comes back 60 miles. So the total distance that she covers is D plus 60. Frank starts out at A, but he falls short. He doesn't get to B. He's short 60 miles. So the distance that he covers is D minus 60. And of course the time that we'll use, T, is going to be from the starting point to the point that they cross paths again. So in that time, Georgia covers D plus 60, Frank covers D minus 60. So now we can set up our two D equals RT equations. D minus 60 equals RT, that's for Frank. D plus 60 equals 1.5 R times T, that's for Georgia. I'm going to rewrite that second equation as the right side is 1.5 times R times T. And now, since the first equation is solved for R times T, I can just plug in. Notice I can eliminate, even though there are 3 unknowns here, I can eliminate 2 of them with one substitution, and I'm just left with an equation with D. So that's very convenient. So I plug that in. I replace RT by D minus 60. That's the substitution from the first equation. So I get D plus 60 equals 1.5 times the quantity d minus 60. We distribute, we get 1.5d minus, and then 1.5 times 60, 1 times 60 is 60, 0.5 is 30, 30 plus 60 is 90. So 1.5 times 60 is 90. Then what we'll do is subtract d from both sides. We'll add 90 to both sides. 0.5 is 1/2. We cancel that by multiplying both sides by 2, and we get d equals 300. So the distance is 300. That's the distance between A and B. This is a slightly harder problem. Pause the video and then we'll talk about this. Kevin drove from A to B at a constant speed of 60 miles an hour, turned around and returned at a constant speed of 80 miles an hour. Exactly 4 hours before the end of his trip, he was still approaching B and only 15 miles away from it. What is the distance between A and B? Let's think about this for a minute. So, in the first segment, going from A to B, he was traveling at 60 miles an hour. Going back, he was traveling at 80 miles an hour. And then starting from B, so from here, from P, all the way to B, and then all the way back to A, that whole segment took 4 hours. So P to B back to A is 4 hours. Well, notice, I'm very interested just in this little interval right here from P to B. We know the distance and we know the speed, so we can figure out the time. The time would equal the distance, 15 miles, divided by the speed, 60 miles an hour. 15 over 60 is 1/4. So that's 1/4 of an hour. We could write that as 15 minutes, but let's actually leave it as a fraction. Well, if P to B to A was 4 hours, and P to B is a 1/4 of an hour, then the route from B back to A has to be, the time has to be the difference. So that is 4 minus 1/4. So I'm going to change 4 into an improper fraction. 16 over 4 minus 1/4 is 15 over 4. And I'm just going to leave that as an improper fraction right now. That is the time. 15 over 4 hours is the time of the trip from B back to A. Well, now we know the speed as well as the time, so we can figure out the distance. And that distance, of course, is the distance we're looking for, the distance from A to B. So the speed is 80. The time is 15 over 4. Remember the great trick, cancel before you multiply. 80 divided by 4 is 20. 20 times 15, well, 2 times 15 is 30. 20 times 15 is 300. And so that's actually the distance between A and B. In summary, when a word problem involves multiple travelers, multiple trips, or a trip with multiple legs, remember that each traveler, each trip, and or each leg deserves its own d equals RT equation. Sometimes you will be able to solve for all quantities in one equation and use those numbers to help solve for other equations. More often, you will have to use the techniques for solving two equations with two unknowns. And we talked about substitution and elimination. If those are new to you, you can find out more about them in the algebra module. Shrinking and expanding gaps. Some motion-based word problems involve two travelers moving toward or away from each other. And sometimes some basic rules can simplify these otherwise very difficult problems. Before I can talk about these basic rules, we have to discuss some terminology. These are 4 basic cases I'm going to discuss here. And in particular, I want to talk about cases 1 and 2. In colloquial language, we'd say that in case 1, that we have 2 cars moving head-on. Sometimes they're moving in this, we'd say moving in the same direction. Case 2, we'd say moving in opposite directions. And I'm going to say that a lot of the colloquial language we have around this is actually a bit distorting, and it makes it hard to understand what's going on mathematically. So I'm going to lump both these cases together and say both of them are cars heading in opposite directions. And what do I mean by that? Well, the green car is heading west. The purple car is heading east. And so in either case, east is the opposite of west. They're moving in opposite directions. In other words, if you point an arrow in the direction of where they're going, those arrows point in opposite directions. And it doesn't matter whether they're getting closer to each other or getting further away from each other. Also notice that it makes sense to talk about these using the same language because they're really part of the same story. If the two cars are heading toward each other, what's going to happen is they're going to pass each other and then keep on moving in opposite directions. So case 1 and case 2 are actually part of the same story. Much in the same way, case 3 and case 4, I'll call those moving in the same direction. Case 3 and case 4 are also part of the same story. Because if the faster car is behind the slower car, it's going to close the gap, it's going to catch up past the slower car, and then later on, it's going to be pulling away and getting further away from the slower car, leaving it behind. Mathematically, cases 1 and 2 belong together, so I will call those opposite directions. The other two I'll call in the same direction. So that's how we're going to talk about these cases. First of all, we'll talk about the two travelers in opposite directions. When two travelers are in opposite directions, we always add the speeds. And this is true whether they're approaching each other, then the sum of the speeds is the speed at which the gap is shrinking. If they're moving away from each other, then the sum of the speeds is the speed at which the gap is expanding. But in either case, we add if they're moving in opposite directions. If they're moving in the same direction, we subtract the speeds, bigger minus smaller. So if the faster traveler is in front, then the difference in speeds is the speed at which the gap is expanding. If the slower traveler is in front, the difference in speeds is the speed at which the gap is shrinking. And again, notice they're part of the same story, that if it starts out with the faster car behind, then later on the faster car is going to be ahead. And in both cases, we're subtracting the speeds. So let's just think through a few scenarios here to make sure we understand this. Scenario number 1, car 1 is going 50 miles an hour south, car 2 is going 70 miles an hour north, and they are approaching. So the velocities are pointing in opposite directions, one pointing south, one's pointing north. So we add the speeds, 50 plus 70 is 120, and they are approaching, so the gap between them is getting smaller, so the gap is shrinking at 120 miles an hour. Scenario number 2, car 1 is going 50 miles an hour south, and car 2 is going 70 miles an hour north, same as before, but now they are moving apart from each other. So now the gap is expanding. We still add the velocity because they're still moving in opposite directions, but now the gap is growing at 120 miles an hour. And notice again, scenario 1 and scenario number 2 could be part of the same story. If we could start in scenario 1, the cars would be getting closer and closer. They would pass each other in opposite lanes, and then later on, they'd be moving further and further apart from each other. Scenario number 3, car 1 and car 2 are both going west. Car 1 at 50 miles an hour, car 2 is 70 miles an hour, and the slower car, car 1, is ahead. So because the slower car is ahead, the faster car is behind, the gap is shrinking, and the speed at which it's shrinking is the difference in the velocity. 70 minus 50 is 20. The gap is shrinking at 20 miles an hour. Scenario number 4, car 1 and car 2 are both going west. Car 1 at 50 miles an hour, car 2 at 70 miles an hour. But now the slow car is behind. Well, now we still subtract, but now the gap is getting bigger because the faster car is in front and it's leaving the slower car behind. So the gap is growing at 20 miles an hour. In a problem in which the gap is obviously shrinking or expanding, we could set up a d equals rt for each traveler, but sometimes it saves time to set up a d equals rt equation for the gap itself. If we figure out the speed at which the gap is shrinking or expanding, we can relate the two individual speeds by simple addition or subtraction. And this is a big, big strategy for this kind of problem. Here's a practice problem. Pause the video and then we'll talk about this. A car and truck are moving in the same direction on the highway. The truck is moving at 50 miles an hour and the car is traveling at a constant speed. At 3 p.m., the car is 30 miles behind the truck, and at 4:30, the car overtakes and passes the truck. What is the speed of the car? Well, first of all, we'll focus on the gap. And the gap, we know that in a time from 3 to 4:30, so that's an hour and a half or 1.5 hours, the gap shrunk from 30 miles down to 0. And we'd like to know the speed. And so that is 30 divided by the time of 1.5, or 30 divided by 3 over 2. We can rewrite that as 30 times 2/3. Cancel the 3's, we get 10 times 2, which is 20. So the gap speed is 20. In other words, the gap was getting smaller at a speed of 20 miles an hour. Well, that must be the difference in the speeds. And so if the truck is moving at 50 miles an hour, the car must be moving 20 miles an hour faster than the truck. So that must be 70 miles an hour. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so City J is 480 miles north of City K. At 10 a.m., car M starts driving south, and car N starts driving north, and it's going twice as fast as M. Both cars maintain constant speeds, and they pass each other at 2 p.m. going in opposite directions. What is the speed of car N? So notice that it's going to make a lot of sense to focus on the gap. The gap goes from 480 miles to 0 in 4 hours. So at 10 a.m., those two cars are 480 miles apart. 4 hours later, they are 0 apart. They're passing each other going in opposite directions. So the gap goes from 480 miles to 0. So we can figure out a gap speed. The speed of the gap would be 480 divided by 4 is 120. So the gap is shrinking at 120 miles an hour. Now, because the cars are moving in the opposite direction, we know that we add the speeds. So the speed of M plus the speed of N equals 120. But we know that N is twice as fast as M, so we can plug that in. R sub M times 2 times R sub M equals 3 times R sub M. That equals 120. Divide by 3. We get the speed of car M is 40, and our N is going double of that. So our N is going 80 miles an hour. So we go back to the answer choices and choose 80. Here's a tricky problem. Pause the video and then we'll talk about this. Cars P and Q are approaching each other on the same highway. Car P is moving at 49 miles an hour and car Q is moving at 61 miles an hour. So they're going in opposite directions. At 2 p.m., they're approaching each other and are 121 miles apart. Eventually, they pass each other. At what clock time are they moving away from each other and are 44 miles apart? So this looks like a really, really hard problem. But notice that the whole thing is in the same case of cars moving in opposite directions. And this is why it's mathematically advantageous to talk about those two cases together, whether they're moving toward each other or away from each other. They're moving in opposite directions. So the gap is shrinking at the sum of their velocities. 49 plus 61 is 110 miles an hour. So that's the speed at which the gap is shrinking. So it's shrinking at that speed when they're moving toward each other. And then it's expanding at that speed once they pass each other. But really, we can add both those distances, but in both cases, it's the same gap speed. In one case, it's getting smaller, one case, it's getting bigger, but it's the same speed. So we can just add those distances up. 121 plus 44 equals 165. And then for time, time is just distance divided by speed. So 165 divided by 110, both of those numbers are divisible by 11. So when we divide by 11, we get 15 over 10, or 1.5 hours. And so 1.5 hours later is when they're 44 miles away from each other. 1.5 hours after 2 p.m. would be 3:30 p.m. So we go back to the answers and choose answer choice B. Going in opposite directions, we add the velocities. Going in the same directions, we subtract the velocities. Think about the directions to determine shrinking and expanding, and solving a d equals RT for the gap can enormously simplify such problems.
Work problems. Some word problems concern machines or workers and how fast they can get certain jobs done. The fundamental equation for this is remarkably similar to the d equals RT equation that we saw in the motion problems. The work equation, I'll write this as A equals RT. A is the amount of work done. R is the work rate, the rate at which work is done. T is time. Some people remember this as art. Any kind of work, it's a sort of art that you're doing. That helps some people to remember the equation. The amount A can be products manufactured, or houses painted, or pizzas made, etc. The work rate could be the number of products per minute, or houses per day, or pizzas per hour, etc. So different work rates would be expressed, obviously, in different amounts of time. As with the d equals RT equation, it's important to be able to solve this equation for all three variables. A equals RT is already solved for the amount. If we solve for the rate, that would be rate equals A over T. Or if we divide by R, then we'll get the time equals the amount divided by the rate. And just as it's important to switch between those three forms for the d equals RT, it's also important to switch between these three forms for the A equals RT. There are two broad categories of work problems. One type involves using proportions. Of course, the work rate, like any rate, is a ratio and can be used to set up a proportion. For background, see the rates and ratio and rates lesson in the percents and ratio module. If you haven't seen that lesson already, I highly recommend taking a look at that lesson first. The other type involves multiple machines or workers working at different rates and figuring out how much work these get done together or apart, something along those lines. Here's a practice problem with the first type. Pause the video and do this without a calculator. A machine working at a constant rate manufactures 36 staplers in 28 minutes. How many staplers does it make in 1 hour and 45 minutes? So this looks like it could be challenging to do without a calculator. And if you did this without a calculator, you might have found yourself working with very big numbers. Let's talk about how to avoid running into such big numbers. So, first of all, I'm going to change that time to 105 minutes. So everything is in minutes now. So we're going to set up a ratio, staplers over time. So 36 over 28, that's the initial ratio that we're given. And this is going to be S, the number of staplers, over 105 minutes. Well, first of all, it would be a mistake to cross-multiply right here. To cross-multiply, do 36 times 105, then 28 times S, and then trying to divide that gigantic number by 28. That would be a nightmare. Please do not make a mistake like that. So do not start by cross-multiplying all those big numbers together. Instead, simplify the fraction on the left. That's a very good place to start. 36 and 28 are divisible by 4. Cancel the 4. We get down to single-digit numbers, 9 over 7. Much better, but we'd still like to cancel more to make that 105 smaller before we cross-multiply. Another huge mistake, we cannot cross-cancel between the 9 and the 105. That is an absolute nightmare, wrong thing to do. And many people think that you are allowed to do that. Now, if this is all brand new to you, I would suggest go back and watch the video Operations on Proportions, where we talk about this in great detail. Instead, we can cancel the 7s, a factor 7 in the two denominators. So we're canceling across the denominators. And again, if this move is unfamiliar to you, go back and watch the operation with proportions. That's really an important video to understand if what I'm saying about proportions here is not familiar. So we cancel the 7s, and we get down to 9 over 1 equals s over 15. Well, now it's ridiculously easy. Now we can cross multiply. We get s equals 9 times 15, so s equals 135. This is 135 staplers. So notice that once we did enough canceling, it was very easy to do without a calculator. If you know the legitimate operations with proportions, and you remember to set up the ratios with the matching units on both sides, so stapler over time, then there aren't many curveballs the test can throw you with these proportion questions. They're relatively straightforward. The other type with multiple work rates can be more confusing if you're not familiar with it. So pause the video and think about this problem, then we'll talk about it. Okay, to detail a car means to clean it thoroughly inside and out. When Amelia and Brad detail a car together, one car takes 3 hours to detail. When Amelia details the car alone, one car takes 4 hours. How long does it take Brad working alone to detail one car? If you don't know the secret to handling this question type, these questions can be confusing because most of the simple arithmetic operations one might try don't lead to the correct answer. The secret to problems involving different machines or workers working at different work rates is this. The combined work rate of people or machines working together is the sum of the individual work rates. In other words, we add the rates. We can't add or subtract the times. We can't add or subtract the different amounts made in different times. Those are the numbers usually given in the problem. We have to construct the rates and add or subtract them. Very important. So we'll go back to the question, and the rates that we're going to look at are cars over hours. How many cars per hour? So the rate of A and B together is a rate of 1 over 3, 1/3. They do one car in 3 hours. And Amelia working alone has a rate of 1 over 4. That's her rate. And so it must be that when we add the two individual rates, they add up to the combined rate. And so that means that Brad's rate alone, that must be the combined rate minus Amelia's rate alone. And so that's going to be 1/3 minus 1/4. Find a common denominator, subtract, it's 1/12. So Brad works at a rate of 1 car in 12 hours. So in other words, it takes him 12 hours to detail a single car. So that is how we solve an equation like that. Here's another one along these lines. Pump X takes 28 hours to fill a pool. Pump Y takes 21 hours to fill the same pool. How long does it take them to fill the same pool if they are working simultaneously? So pause the video, think about this, and then we'll talk about this. Again, what we need to do is figure out the rates and then combine the rates. So here the rates are going to be in pool per hour. So we're talking about the same pool, that single pool in how many hours. The rate of X working alone is 1 over 28, one pool over 28 hours, and Y working alone is 1/21, one pool in 21 hours. We're going to get the combined rate by adding those two individual rates. So we're going to add them. In order to add them, we're going to find a common denominator. Notice that 28 is 4 times 7, 21 is 3 times 7, so we'll multiply the first one by 3 over 3 and multiply the second one by 4 over 4, and that will get us to a common denominator of 84. That is the least common denominator, the least common multiple. When we add in the numerator, we get 7 over 84, That cancels down to 12, so that is the combined rate. So that means that they're working together, they do one pool in 12 hours. So it takes them 12 hours together to fill the pool. For work-related word problems, use A equals RT. A is the amount, R is the work rate, T is the time. For proportion-related work problems, you need matching units on each side, and you need to understand the operations with proportions. For problems with multiple workers or machines, create rates for each one, and then add the rates. Growth and decay. Some word problems concern populations or samples that are in the process of growth or decay. Human populations and populations of animal or bacteria experience natural growth. Decay can include radioactive decay, something melting, a bacteria population getting wiped out, etc. This is an extremely rare question type, so chances are relatively low that you will see this question. And another important idea, these questions may refer to some specialized scientific ideas, such as radioactive decay. You do not need to know anything about the underlying science. All the mathematical information you will need will be given in the question itself. The basic format of this question is you will be given some starting value and told that the size gets multiplied or divided by a certain quantity in some fixed interval of time. Then you'll be asked for the resultant amount after some slightly longer period of time. Take the calculations one change interval at a time. Whatever time interval they give in the question, use that time interval as a step and just move by those steps. Step by step, figure out the amounts until you arrive at the final amount. Here's a practice question. Pause the question, and then we'll talk about this. Okay, when isotope QXW radioactively decays, it loses exactly half its mass in each 3-day period. So that's our step interval, 3 days. Suppose scientists start with a 96-gram sample of a pure isotope of this on a certain day. What will be the remaining mass in 12 days? So step by step we'll move. So at the start we have 96 grams. 3 days later, there's half of this left. So there's 48 left. Another 3 days later, there's half of that left. That's 24. Another 3 days, there's half of that. And finally, another 3 days, that puts us at 12 days now, there are 6 grams left. And that's the answer. Here's another problem. Pause the video, and then we'll talk about this. Okay. So we have some kind of bacteria, and it multiplies the size of its population by 5 halves every 4 hours. 4 hours is the time interval step that we're going to take. So there are 24 billion at 9 a.m. and optimal conditions are maintained. How many are there at 5 p.m. of the same day? So we're going to step 4 hours at a time. So we're going to start at 9 a.m. We're going to 24 billion. 4 hours later, we multiply 24 by 5 halves. Well, canceling the half, we get 12 times 5, that's 60. Then 4 hours later, we're at 5 p.m. 60 divided by half is 30. So that will be 150 billion. So at 5 p.m. of the same day, there are 150 billion of these bacteria. If you happen to see a growth or decay problem, don't panic. You will be given the multiplier you need, and all you need to do is follow the calculation step by step, one change interval at a time. Mixture problems. Some word problems concern mixing solutions of various concentrations. What exactly does that mean? I will give an extremely concise introduction to some chemistry that may help you make sense of this topic. First of all, it's a fact that many different materials in nature happen to dissolve in water. This forms a solution when something dissolves. And it's a fact that chemists often dissolve these materials, they could be salts, sugars, acids, and bases, in water. The dissolved substance is called the solute. The concentration indicates how strong the solution is. That is, how much solute is dissolved in a given quantity of water. On the test, concentration will always be expressed as a percent. So concentration equals the total amount of solute divided by the total amount of solution, and this is times 100%. Notice that concentration is not the ratio of solute to water, but the ratio of solute to the total amount of solution. That is the amount of water plus solute. So it's not the ratio of the two materials involved, it's solute to the whole. That's what constitutes concentration. Some other details, just things you don't have to worry about, but just so you know you don't have to worry about these. Sometimes concentrations on the test are given as a percent by weight and sometimes by volume. This will be consistent, so you don't need to pay any attention to that. You could ignore that. Sometimes rather than water, scientists use some other liquid, alcohol or something else. That material happens to be called the solvent. It doesn't matter what the solvent is. It doesn't change anything about our calculations. So all those are things that if you notice them, you don't need to worry about them. They don't matter. Okay. Here's a very easy question. Pause the video and then we'll talk about this. Alright, so HCl, and again, all these chemicals that are mentioned, you don't have to have any idea what they are. As it happens, HCl is hydrochloric acid. How much HCl and how much water must we use to create 5 liters of a 30% HCl solution? So this is a very basic question. So the amount of HCl would be 30% as a decimal, 0.3, times the whole, which is 5 liters. And when we multiply out, we get 1.5. So in other words, we're going to need 1.5 liters of pure HCl, and that means that the rest of it, which would be 3.5, has to be water. So 1.5 is HCl, 3.5 is water. We combine those, we get a 30% HCl solution. Now this question by itself is far too elementary to be a test question, but you will need these skills in more complex problems. This is much like we saw in distance, rate, and time problems. Just given a simple, here's a distance, here's a rate, find a time, well that's too easy. That's not going to be a question by itself, but that is a skill you would need in solving a larger question. And much in the same way, you will need these skills in solving a larger question. Here's another practice question. Pause the video and then we'll talk about this. Suppose we start with 5 liters of a 30% HCl solution. How much water must we add to create a 20% solution? Alright, well this is interesting. So the first thing we're going to figure out is how much solute do we have. Again, 30%, which is 0.3 times 5, we have 1.5 liters. And of course that's not going to change if all we're adding is water. So we're going to have a new amount, and it's going to be 20%, and it's going to have the same amount of HCl in it, the same amount of solute in it. And so here we need to solve for x, and that will be the total amount of solution. So of course 0.2 is 1.5, multiply both sides by 5, we get 7.5 liters. And so the old solution was 5 liters, the new solution is 7.5 liters, so the difference is 2.5 liters, and that's how much extra water we need to add to bring this from a 30% solution to a 20% solution. In that problem, we added water to the solution to make a less concentrated solution. Notice we could also add pure solute to a solution to make a more concentrated solution. The test could ask about either of those scenarios, but the most common questions involve mixing two solutions of two different concentrations. So here's a practice question along these lines. Pause the video and then we'll talk about this. Okay, again, you do not need to know what that chemical is. HCPO4 that happens to be phosphoric acid. It's an ingredient in Coca-Cola. But at any rate, suppose we start with 8 liters of a 60% solution. We add 4 liters of a C% solution. So C is the unknown, and the result is 12 liters of a 50% solution. What is C? Well, the first thing I'm going to do is figure out how much solute did I begin with and how much solute did I end up with. So in the first solution, I had 4.8 liters of solute. In the resultant solution, the final solution, I had 6 liters of solute. And that means that the amount of solute that was added, that amount of solute was 1.2 liters. So let's think about this. There's 1.2 liters of solute in that 4-liter solution. So we just have to figure out 1.2 is what percent of 4. So divide this out, and we get that this is 30%. And so C equals 30%. Sometimes in solution problems, if amounts of 2 different solutions are initially unknown, we have to set up simultaneous equations. This is probably the most popular solution problem type that you'll see on the test. One equation will always be a total equation, that is the total volume or the total mass or weight. The other equation will always be about the amount of solute. So those are the 2 equations you're always going to set up, and once you have those 2 equations, you use the techniques for simultaneous equations. Here's a practice question. Pause the video and then we'll talk about this. Okay, here we have a question about H2SO4 sulfuric acid. You don't need to know about that. Suppose we start with unlimited supplies of a 20% solution and a 50% solution. We combine X liters of the first with Y liters of the second to produce 7 liters of a 40% solution. What does X equal? So clearly, X plus Y equals 7. That's one equation that we have. We have X liters of the first thing, Y liters of the second thing, so X plus Y equals 7. That's one equation. So what we're going to do is focus on the solute. The X plus Y equals 7, that's the total equation. The solute, well, the resultant solution is 40% of 7 liters, so that's 2.8 liters of solute. All right, so our total equation is X plus Y equals 7. The solute from 1 is 0.2 times X. The solute from 2 is 0.5 times Y. We add those 2, and it should add up to the total solute. So that's our second equation. Our first equation is X plus Y equals 7. Our second equation is this solute equation, 0.2X plus 0.5Y equals 2.8. So in that first equation, what I'm going to do, I'm just going to solve it for Y. The reason I'm going to solve it for Y is that when I substitute, that will eliminate Y, and it will leave me with an equation for X, which is what I want. So I'm going to plug this into the equation, into the second equation, substitute it in. I'm going to multiply everything by 10 just so I don't have to deal with decimals. I'm going to distribute, collect the terms, simplify a bit, subtract 35 from both sides. We get negative 3x equals negative 7. Divide by negative 3. We get x equals 7/3 liters. And that's the answer to the question. Concentration is the ratio of solute to the total solution, most often expressed as a percent. And here, of course, we have to be very fluent in going back and forth between percents and decimals. We can change concentration by adding water or adding pure solute to a solution, or by mixing 2 solutions of 2 different concentrations. If we mix 2 solutions in unknown amounts to get a known total of a known concentration, we set up simultaneous equations. One equation is the total amount equation, and the other equation is for the amount of solute.